Good morning, good afternoon, good evening. I understand we may have people throughout the world possibly watching this. I appreciate your time in coming here and listening. If not now, then possibly in the future. But what I'm about to share with you today is something that I feel is a new technology and new application for seawater desalination. That has been my research focus within the last year. Primary driver of this technology, what I'm about to present, is biofouling remediation for reverse osmosis seawater desalination membranes. If you're familiar with this technology, it's basically drawing in seawater and taking out the essentially 97% of pure water and generating freshwater resources for several areas such as Saudi Arabia and Southern California, where I am, in Australia, and many areas where there are water deficits. It's a thermodynamically efficient process. However, the biggest problem of this process is biofouling and the process of bacteria and the attachment mechanisms and the affinity that bacteria have for RO membranes. It eventually generates a biofilm, which dramatically increases the hydraulic resistance of the membranes up to 20%. And these are very energy-intensive processes that, as hydraulic resistance goes up.
Errol, sorry, I think you forgot to advance your slide.
Oh, my apologies, Vladimir. So, I just wanted to kind of generate a little background knowledge on it. The unique concept or the application of dielectrophoresis, what I'm going to present, is unique to seawater desalination. This slide that you see here is a very general representation of on the left you see seawater comes in. There's pre-treatment processes following this, and this is very intensive. This is trying to remove as many of the particulates and various colloidal matter that you find, finer particulates in seawater before it gets to the reverse osmosis membrane modules that you see circled there. And this is the primary energy deficit, and especially with biofouling. So my lab at University of California, Irvine, is primarily focused on developing technologies, all across the board, from salt, pulse injections to different, gradients of bacteria formulations that will feed or deter the eventual formation of biofouls. And my aspect on this biofouling and remediation is numerical simulation with the help of QuickField. The primary research drivers of dielectrophoresis thus far have been cancer research and protein separation science, DNA sequencing, nanotube development research. So this application that I'm about to present to you is very unique when it comes to seawater desalination. So let me see. Let me click the next slide. So basically, dielectrophoresis is the movement of neutral polarizable particles in an homogeneous electric field, which essentially is, which describes bacteria. Bacteria do not have positive or negative charge on there, and there's not an ionic charge on these particles. So the application of dielectrophoresis is very possible. It's the forces that we need to determine if it's a realistic approach. And so the force does not require the particle to be charged, as I said. All particles exhibit DEP reactions in the presence of electric fields, all dielectric particles. And the strength of the force depends on the medium and the particle's electrical properties. And what better way than to use QuickField in determining these forces, and we'll see in later on the presentation. Sorry about my computer is. I'm waiting for my slide. There we go. So early in my research, I generated, I dove into the field of dielectrophoresis, which was essentially discovered in the 1950s by a Professor Pohl from the University of Oklahoma, and did a lot of the initial research on this, and kind of generated some discussions with other lab groups at the University of California, in particular the biomedical engineering department. And I did a lot of collaboration with them, one of their PhD students, and their focus is cancer research. What they essentially have discovered is healthy cells and cancer cells. And if you understand the science of dielectrophoresis, this is not, a terrible, remarkable discovery, but they definitely have different dielectric properties. And the concept being you can essentially filter cancer cells from healthy cells and remove cancer cells. And so their research has come a long ways, and it's progressed quite a bit. And essentially, I want to do the same thing. I need to remove bacteria, particles, cells from the reverse osmosis membranes, and understand the forces involved. So, and this is just a little quick snapshot of the work being conducted at UC Irvine. So when I investigated, my all the different applicabilities and concepts for dielectrophoresis, I did find, in fact, that there was one paper that was published in 2009 by a group. It was a joint effort from Israel and Germany, and they studied the application of a membrane, as you see the red circle, and with the membrane, there's a thin line right through the, and this is a cross section of the membrane. So you have a suspension up top, that's the inlet feed stream coming up from up top. Number 2 there is the pump. So you have a peristaltic pump that introduces the feed stream to upper right of the microchip, and then the feed stream goes from right to left, and the retentate is the waste stream, and then the permeate is the clean water. So basically, you have from right to left, you have the water going through the permeable membrane only to water, therefore generating your clean permeate water stream, and then your retentate is your waste stream. And what essentially they want to do is generate a negative dielectrophoretic force on the particles to push them away from the membrane, essentially removing the possibility of bacteria attachment on the membrane, which increases biofouling. I want to stress that. So this is the general layout, and they applied a AC voltage of 200 volts. And on the upper circle to the right of the highlighted section, you have the number 6 is the insulated plastic material around the electrode. Number 5, number 4 is the electrode, and 3 is the permeable membrane, only to water. So next slide. So here are the results of the. When I saw these results, I was a little disappointed. And what you see on this image is the actual clay particles. So they used solid clay particles, and they ranged from anywhere from 5 microns to 200 microns. And I think 200 microns was the average. Was actually the average size of the clay particle. And utilizing the difference in dielectric properties of clay and water, and they conducted this research. The top is without applied DEP, and the lower is with applied DEP. And you think, from the theoretical aspects of applied dielectrophoresis that it would be 100% removal, when in fact it is far from 100% removal. And I wanted to investigate, or I wanted to understand better why did this research show up so inconclusive, because the theory is there. The theory is it should, more than adequately remove the possibility of attachment, and specifically with clay particles, which have a lot larger differential as far as dielectric properties between bacteria and in clay with respect to the water medium that exists. So hence my my resolve in finding QuickField. I've been through all the journal papers, well, not all the journal papers, but quite a few journal papers, and a few of the texts at the UC Irvine library. And I found a book, a joint effort with Dr. James Claycolm and QuickField, and he had a lot of interesting, he's done a lot of interesting work, especially with applied dielectrophoresis, and he does have some published videos with QuickField. And I started to investigate the possibility of maybe applying numerical simulation and understanding better how the electric fields and the various properties of particles and colloids, such as bacteria or clay, such as the published journal article. And obviously doing brute examination for Maxwell's equations is very difficult, and the beauty of QuickField certainly increases the certainty level of results and reduces human error. So Coulombs Law basically generates the force between two particles in free space. That's not really an applicable slide. But here essentially is the dielectrophoretic force. This force will tell us, given the potential between the two electrodes, and the 2 pi r cube component is a spherical component, so we're assuming a perfect sphere. The electric M is the medium for water, and RE is the real component based on the dielectric properties between the particle P and the dielectric property of the medium, and this difference is between 1 and negative 0.5 if you run through that. So that's and then the gradient and E squared. Gradient being the depth of the electric field, the change, and E squared is your potential. If you have any questions, certainly please. And hope I'm not. Am I going too fast with this, Vladimir? Okay.
I think it is okay. It's interesting, and actually
Okay.
You could go with your pace, whatever is comfortable for you.
Okay. All right. So here essentially is a good summation of what I've already kind of discussed. The suspended particles of water, the dielectric constant is less than the dielectric constant of water, which we all know is around 80 for standard temperature. Consequently, these particles are repelled from regions of high electric field intensities. This phenomenon is called negative DEP, and essentially what I'm trying to model to repel attachment to that membrane that we saw earlier. It is notable that most aquatic colloidal dispersions, the dielectric constants of these particles are significantly smaller, typically less than 10. So the difference between 10 and 81, as we saw in this earlier slide, that will help us generate a negative DEP. So it's a unique application as far as seawater, given seawater, and which is different than cancer research, because blood and cancer cells, the difference between they typically work in a positive DEP based on this real component of the Clausius-Mozadic vector. So an appropriately designed electrode array located next to or under a membrane can generate regions of high field intensities that will repel particles in suspension away from the membrane. This is essentially what I'm trying to model. So what I've done with QuickField and the incredible patience of Vladimir and Alex, a few others, they've helped me tremendously in trying to generate my electrode geometries and how to properly set up boundary conditions. And I've been learning AutoCAD and utilizing the power of AutoCAD and importing the geometries into QuickField. I can generate simulations and try to better understand what geometries are better for this unique application. So here we kind of have a three-dimensional view of that paper that we saw earlier. So I think this kind of, I've been looking at this stuff for a long time. If everyone that's watching, I hope this makes sense. But the lower, the bare electrodes in the red, and then you have the membrane in green, and then you barely see above there is the clay particle that they used in their journal, and then the insulated electrode in pink, and then the square electrode is denoted in the top there. So and then I just took a slice using AutoCAD. Just took a slice and imported it into QuickField. These are just the equations of motion. These are not complete. This does not take into account the Joule heating effect, and I do need to work on this component. This is incomplete. But at this moment, essentially you have the dielectrophoresis force minus viscous drag, and then on the Y component you see at the end there's a buoyancy factor. But that is relatively mute with respect to bacteria. For clay, it is applicable, but for bacteria, it's not so much. So here is a cross section that I imported or exported from AutoCAD into QuickField. You can see here these are the kind of the tolerances and general layout. So the square electrode up top is 1 millimeter in width, and height is half a millimeter. The three electrodes on the bottom are half a millimeter in diameter. There's that membrane on the bottom, and then the distance is 1 millimeter. So these are the electropermittivity and dielectric properties of the acrylic glass, which is in pink there. Then the clay particle, membrane insulation, seawater, so forth. Importing that into QuickField, as I said earlier, generating the mesh, which only takes less than a minute, actually a matter of a few seconds. It generates the mesh, and then we can go ahead and use LabelMover to generate results, which I'll show a little later here. So yeah, here's the acrylic glass, the plastic insulation around the square electrode. This is the membrane. I'll highlight it in. Oh, talking too fast. I'm sorry. This is the membrane. Here's our seawater, and this is like a profile view now. So the particle is traveling out of the screen towards us. Okay. So, and another thing with simulating microchips such as the one I'm doing is I've neglected the end effects. So inlet and outlet effects are it gets into fluid dynamics heavily, and that component is more of a three-dimensional analysis that I'm looking to do later in MATLAB. But this research cannot go further without the assistance of QuickField and determining the mechanical forces that are generated from the potentials and the geometries of the electrodes, and how to maximize these geometries and potentials is what I am hoping to do with QuickField, and thus been quite successful. So after doing the mesh analysis and then running the problem, you can see here that there's you can do a zoom in on the actual clay particle. So you have, in the center there, you can see the blue. That is our clay particle, and you have to zoom in quite a few times to get to a 5 micron. It gives you the scale of and the capacity of QuickField. So you have a very large microchip geometry, and then you can scale into 5 micron and do a relatively accurate analysis of a particle such as clay or bacteria or whatever, depending on the properties. So it's just a zoom in. So here is the actual paper, and when I simulated using QuickField, the force generated, the negative DEP force generated in that clay particle in the center of the earlier screen was only on the order of 10 to the negative 20, which is slightly below viscous drag effects. So it's almost mute, and the electric field primarily is generated above their microchip there. So they actually were not really generating any sort of negative DEP force like that they were hoping to, and so this better explains their early results with applied DEP, or so they claimed, or so they were hoping. They actually were not, because given the dielectric properties and the permittivity value of the insulation was actually removing and funneling away the electric field. And in the paper, they describe why they wanted to use insulation is from a electrical safety factor, that they didn't want the connectivity of water, and there was a safety issue that they surrounded it by the insulation. So that's why they applied this. So what you can do, obviously, in QuickField, if you're familiar, you can change the permittivity values of the medium, and on the left there you see you have a much greater electric field force generated than on the right, which is what they actually did in their experiment. And you can vary all the different properties of the materials. So here is a zoomed in image of the two-shell ellipsoid model of the bacteria, and the inner membrane and the perismatic membrane space of the bacteria. And this aspect of my research is far from complete, but it is certainly beginning. And the aspect ratio of bacteria and the arrangement of the bacteria within the electric field has many variations and possibilities, not including the motility of bacteria and the flagella of bacteria. But so that would certainly change the equation of motion. But fundamentally, this is the geometry. It's it's about 10 microns and 2 microns in width there. And you can barely see the membrane, but I wish I had a better image of that. And this is these are the generated mechanical force results that I got from QuickField using LabelMover. I was able to move the bacteria modeled from 0, being from the square electrode on the bottom there, to 1, which is essentially at the membrane. And so we were able to generate a maximum a negative DEP force closest to the membrane, which is what we're hoping to do. and verified this using QuickField. Obviously, the aspect ratios and geometries are the potential for these are many, and to model a bacteria like this is certainly incomplete. And I've neglected motility, which is a fairly significant factor. And then this kind of just shows the development of microfluidics to date. And this doesn't include from in the 50s when Pol really started the intensive research in this field. But over the years, it has gone up significantly and continues to rise. And this is particularly important for seawater desalination because you have megaliters per day being produced from these units. How could a 8-liter per hour unit be applicable? So certainly scalability is an issue that needs to be resolved, but in its infancy and scientific demonstration or feasibility study with a QuickField, I think we can proceed further, and certainly has potential.